Here is the second video for mathematical proofs. We got proof by contradiction. And most people don't find this one as bad as exhaustion, but it can still be kind of frustrating, but it's usually a bit quicker. So for these ones, we are essentially searching for something that's going to disprove a statement that assumes that it's always right. So like this guy here. And we're essentially just searching for anything that's going to make this bit right here just not true. So we just start plugging in some numbers and see what we get. And you put some numbers in and you're like, oh my goodness, they're starting to get here. We've already done, 5 whole examples and you're starting to get tired of this. So you're like, okay, there's got to be a cleverer way, right? And there is. And so you're like, well, this 11 is the thing that's going to be the thing that gives the counterexample. So if you just make this part a factor of 11, then it's not prime, right? So we just throw 11 in. That gives you 253. So what we would then do is just say, okay, well, that thing divided by 11, and you check your calculator, and that's going to give you 23, right? So therefore, this one here is a counterexample, and you would therefore put your final statement there. So sometimes it's not a bad idea to just throw numbers in it like it is at the start, but you can go for a while if it's just by rote and you just plop in one number in. So it's probably a better idea to see if you can think right away if there is something that you can do to just toss it in right away. Like quite often it's if there's a term here, that's going to be the key to these disproofs. This brings us to a classical kind of story, legend, myth of hypapsis and root 2. Now, the story is that hypapsis quite often gets credited with the discovery of irrational numbers, but that's not quite clear, right? So there's quite a bit of unknown surrounding this, but here's the story anyways. Hypapsis was a student of Pythagoras here, the guy with a beard. Well, they both have beards, but this guy here is Pythagoras. And this is little Hypapsis studying vigorously beside Pythagoras, looking up to him as an idol, as a lot of people did at the time, and Pythagoras is quite often credited with creating a cult called the Pythagoreans, who believed in the sanctity of numbers and things like this, and were really into discovering the truth behind numbers. Now, Hypapsis was a clever student and kind of got into Pythagoras' way. Now, this is the unclear part. Hypapsis quite often gets credited with multiple things, but the story is that the Pythagoreans believed so much in the sanctity of numbers is that Hypapsis proved that root 2 was irrational, and that angered them so much that Pythagoras drowned his student. Pythagoras gets mad and essentially just throws him off a boat, and Hypapsis can't swim and essentially drowns for figuring out that root 2 is irrational. Now, this is quite often said to be a myth, and that the real lesson is that trying to overreach or to go into the things that can be unproven or irrational realm is to overreach, and therefore the gods would punish you for being too clever or trying to go too far beyond what mortal men should and should not do. Anyways, we'll never really know, and so let's just go through the actual proof of what caused this story in the first place. So the idea is that we're going to say that if root 2 is not irrational, therefore it's going to be the combination of some whole number divided by another whole number, and these are indivisible, right? So that was the idea, is that every number was made up of these two pieces of indivisible parts, but root 2 doesn't, which we know, but this is the proof of it. Okay, so we assume root 2 is rational, and a and b are positive whole numbers with no shared common factors between them. Now that's the key issue right there, so that once we whittle down and reduce everything, eventually it'll come down to the point where you cannot reduce this any further because they don't have any more common factors, okay? So that's the assumption. We're going to do this, prove that this is not true, so proof by contradiction. Okay, so we get these first two steps. You square both sides and you get 2 is equal to a squared over b squared, and therefore we get 2b squared is equal to a squared, but that means that a squared is even, right? And the only way for something to be even is if it can be broken down into divisible by 2, right? So a itself must be even, because if you squared something even, it's still going to be even. And thus this implies that a is 2 times a number where m is a whole number here, so it's even, right? Right, so we had 2b squared is equal to a squared, and then we found that a is going to be 2m. So this therefore implies, if we put those two back together, that 2b squared is equal to bracket 2m squared. And you can probably see where we're going with this. So this implies that 2b squared is equal to 4m squared, which then implies if you divide both sides by the 2 there, that b squared is equal to 2m squared, which by the same logic implies that b is also even, right? So then if we look back at the first assumption that a and b are both indivisible, or they can't be reduced any further, this becomes untrue, right? Because if b is even, b is going to be therefore implied to be something like 2k, where k is a different whole number. And then if you put that back into the original, where you get root 2 is equal to a over b, but then we said, well, a was 2m and b was 2k, and therefore they share a common factor. So a common factor of 2, which breaks our original definition of a rational number here, right, where you had a over b and that was indivisible. You couldn't reduce it any further than that. Therefore, the only thing left, the only other part, if it's not rational, it must be irrational, and therefore root 2 is irrational. Proof by contradiction, drown your student kind of thing, right? So that's where that story comes from, and this one's a classic proof. They do it with other numbers too, so other irrational numbers. You can kind of get the same idea through there and go through the same logic of it. I think root 5 is used quite often as well. But so those are your proofs. That root 2 one is going to be mostly at the end of your second year. That type of logic is where you're aiming for. So don't worry if can't get that right away. It is a trickier one. Anyways, that's enough for proofs for right now. And if you like this video, please subscribe and give it a like. Okay, bye-bye.